So bonding is done through electrons. And ionic bonding is a transfer of electrons, and covalent bonding is a sharing of electrons. See if I can make this bigger for you. So here we have an S and P sublevel. And if we take something, for example, that only has S's, well, like hydrogen, so what would happen is basically we would have an overlap of their S orbitals, and the electrons would be somewhere in between them. That would be that hydrogen bond. When you have more complex shapes, sometimes you need all of your S and your P orbitals together. For example, this would be linear. The next one would be, I believe, trigonal planar electron arrangement. So with trigonal planar electron arrangement, you could have something like a boron working this. Boron, well, it could have 3 valence electrons. So that would be sp2, what we call sp2 hybridization. What that means is that the S and the P orbitals basically form something like this. So that would be sp2 hybridization. You have 2 basic areas where the electrons are concentrated. This could also occur with carbon. Here we have sp2 hybridization. Basically, you count the areas where bonded atoms are. So if it's sp2 hybridization, it has a trigonal planar arrangement. Keep in mind, I am saying the word arrangement here. I'm not saying that it is a trigonal planar, I can't spell, arrangement. This includes trigonal planar and bent. But let's say it only has 2 areas. Oh, why did I do that? You should have been a C. Then we would say it has sp hybridization. So what's the best way to do this? sp2, this would be sp. Anybody give me another way that it could be sp? Hydrogen cyanide. 1, 2. 2 electron arrangements, sp. So a lot of times sp, you have either double bond, or single bond, triple bond. This is not the S like hydrogen goes through. We would not call that sp because that is just 1 bond. This is something in the center and then 2 electron arrangements around it. What do you think the next one is? We have sp, we have sp2.
sp3.
sp3.
Would that be like CH4 and stuff like that?
CH4, CCl4. And basically, yeah. So the H's sphere or s orbital goes and collects those electrons from the sp3. Again, all you got to do is 1, 2, 3, 4. sp3, right? That is tetrahedral arrangements. The biggest thing that people mess up on this is they see something like water and they want to call that sp hybridization. It's not, because remember, it's the arrangements. There's still electrons up here. So it still looks like this, sp3 hybridization. It's tetrahedral arrangement, but it's bent geometry. What's next? It comes after our p orbitals.
D orbital.
B. So if we have sp3 d1, well then we have we have to have something that's third energy level, third period or more.
Could it be PCl5?
Let's do it. I'm just going to put the P there, but what we have then, PCl5. So we have top, bottom, out that way, and out that way. What is that? 5 bonds, 0 unshared pairs.
Trigonal bipyramidal.
Trigonal bipyramidal arrangement. Two things that I'm terrible at is math and spelling. Sorry about that. And handwriting. I was unsatisfactory all first 3 primary school years. So trigonal bipyramidal arrangement. I'm going to write arrangement every time here so that we understand that this not only stands for sp3d1 for trigonal bipyramidal, but it also is for the shape of seesaw and T-shape and even linear if you have 2 things and then 3 unshared pairs. Last one that we cover, sp3 d2. Again, this has to be third period or greater. So we have, do you have one for this one?
SF6.
SF6. So again, S in the middle. 1, 2, 3, 4, 5, 6. 1 plus 3 is 4, plus 2 is 6. That's all we're doing is we're adding those up. Octahedral arrangement. Is this the class? Yeah. What's her name in here? She got it. We can also call this square bipyramidal, right? Who was that? Is she here today? Nope. Keep in mind that this also could be if you had something that was, I can't think of any now, but if you had something that was square pyramidal, right? You have the thing on top and then this. So there are your atoms, and then you have a lone pair on bottom. As long as you count S, P1, P2, P3, D1, D2. As long as you count them, you should be able to identify all of these. Now, the reason why this becomes important before we go into organic chemistry is organic chemistry deals with a lot of carbon things, and you have to keep in mind your 3-dimensional structure. If something is sp2 hybridization, then it is flat, right? So those are things that will help us get better at the ideas behind this. Now, we have all these hybridizations. When we look at bonding occurring, we need to understand that we have the nucleus. They're coming together. They're attracting the electrons. But if we try to force these nuclei together, that's going to take more energy, right? So there is a very specific energy for this. Let's put energy here. Notice this is positive and this is negative. If we start up here, we go down here and here. This is going to be the radii. This is going to be distance. So this is versus distance. Energy versus distance. If we decrease the distance, like this is 0. If we decrease the distance between 2 atoms, it gets very hard to push them together. Right here, for this particular group, the radii is going to be that part of the line. That is the lowest possible energy that they could have, and it's negative. Well, that amount of energy is the amount of energy needed to pull them apart once they're together. If you take your hands like this and clasp them, it takes energy to pull your hands apart. That's like the bond. So this is negative because we're putting energy into it. This is energy we need to put into it. And then we can get them together. This is called basically bond energy. And if you recall, we're going to figure out the energy of a reaction, or the enthalpy. Remember delta H from last semester. We're going to find out the enthalpy, or the delta H of a reaction, by using bond energy. This is also referred to as bond dissociation energy. What is something that dissociates?
Splits up, or?
You got it. So that is on page 22, right now. So as I said, and I'll let, if you didn't get this, I'll go ahead and write the last thing on this real quick. So if we keep in mind delta H of a reaction is equal to, it's equal to usually the products of formation, formations minus the reactants. But since we have bonds, we are going to take the summation of the bonds that we break, and we're going to subtract the summation of the bonds that we form. So if we break up all the bonds, we have a certain amount of energy. If we form back the bonds of the products, whatever energy we had left from when we broke them will be the delta H of the reaction. Is this darker than normal, the screen? No? Okay, cool. Maybe it's just the way I've got it. It just seems darker to me. All right, so there we go. Now, Emma, I don't know what your time is, but I am recording this one and I'll play it. But if we take a look, I don't know if you got 3 minutes. I can show you this pretty quick. I'm going to go ahead and write this again. So I need you guys to think about what these look like, what their Lewis structures are. And CH4, 2Cl2, delta H reaction equals the summation of bonds broken. It takes energy to break bonds minus summation of bonds formed. Here's the thing. Your biology teacher may have messed up and said, energy is stored in bonds. That's not really true. Basically, you have these bonds, and they have a certain amount of energy because it's just like the planets. Don't the planets pull together each other, right, with gravity? Same thing. These atoms are pulling together each other. When you separate them, they will snap back like magnets or whatever with other things, and it may be of less energy. So there is energy released. So if we take a look, hopefully you got CH4 for this. So how many carbon-hydrogen bonds are there?
4.
4. So we take 4 and we multiply it by the carbon-hydrogen bond energy, which is 411 kilojoules. Then we're going to add it. So how many Cl bonds do we have for Cl2?
2.
So Cl, 240 kilojoules. But here's the problem. This is kilojoules per mole. So even though we have one Cl bond, we have 2 moles of them. So that means we need to multiply that by 2. Plus 2 times whatever FF is, 155 kilojoules. And then we will bracket that whole thing. And then we will just subtract, doing the same thing here. So if we draw that out, you can see I'm only drawing certain ones out because other ones I can do in my head. But think about that for the next one, nitrogen. That one's a little bit different because that's not right there. So we are going to subtract. We have 2 Fs to C. So we come down here, F to C is 485. We have 2C to Cl, 327. We have 1 HF for every HF, but we have 2 moles of that. Oh, dang it. Did I do that right? Yes. Okay, good. What was I talking about? HF, F, and H is 565. And the last one is HCl. We have 2 of them. HCl is 428. So 4 times 411 plus 2 times 240 plus 2 times 155.
Wait, so Mr. Jackson?
What?
So is this kind of like the opposite of what we did when we know the bond, like the heat of formation for like a certain compound?
You got it. This is actually how you would figure out those heat of formations.
Okay, cool. Thank you.
2 times 485 plus 2 times 327 plus 2 times 565 plus 2 times 428.
The answer is 3,610.
2,434 minus 3,610.
That would be negative 1,176.
So the delta H of this would be negative 1,176 kilojoules. Boom. All right, let's take a look at, I'm going to jump down to number 4. So what does 2C2H2 look like?
Isn't it like a double bond between the C's and 1 H attached to each of them?
You got it. So we're going to have to take 2 times 1 double bond between C and C. So that if we look down here, we've got to be careful of that. It's not just a CC, it's a double bonded CC. So it's 602. And it's not just this multiplied. It's a little bit less than this multiplied by 2. That's because the sigma bond is more powerful than the pi bond.
Isn't that a C2H4, not C2H2? You're drawing.
Oh, so it's not a double bond. It's actually a what?
A triple bond.
You got it. For some reason, I did that earlier with the same compound, didn't I? Yeah, for some reason, I can't think whenever I see that compound. Makes me lose my mind. So instead of a double bond there, we need to do the triple bond. And it's not 3 times the single bond here. It's a little bit less, again, because you have a sigma and 2 pi bonds. Remember, the sigma is the handshake and the 2 pi bonds are the hugs. So 835. So we have 2 moles of that. So that's 2 times 835 kilojoules. We have single C hydrogen, 2 single C hydrogen bonds, but we have 2 moles of that. So that's going to be plus 4. 4 times 411. Now, here's one of the keys. Notice if we take a look. O2 down here, 494. They have bonds. Remember when we did heat of formation, we used what for elements in their standard form?
0.
0. We do have bonds with O2 and N3, right? So let's keep that in mind. So here we've got, and we already did it with Cl2. So here we've got 494. What are we going to multiply it by?
5.
I'm going to keep the same, what do you call that? The way you draw mathematical equations. What is that? It's not called writing. Is there some fancy word that they use for it? Same notation. Instead of putting 5 dot that, I'm going to keep using parentheses. I don't want to confuse anybody. Here we have CO2. So we've got two CO double bonds, but we have to multiply that by 4. So that's 8 CO double bonds. 799. Remember, all these are in kilojoules. And then we have H2O. We have 2 of that. So for every H2O, we've got 2 OH bonds. So we'll have 4 total OH bonds. No, H, 459. Questions here? Two times 835 plus 4 times 411 plus 5 times 494.
That would be 5,784.
8 times 799 plus 4 times 440. 8 times 799 plus 4 times 459.
The answer is 8,228.
5,784 minus 8,228.
It's negative 2,444.
Cool. I can't see any mistakes in there. If somebody does, please make note of it. Let us know now before we just move on. But 8, 4 times 2. Yeah, all this looks good to me. Unfortunately, I don't have the key for this one right now, but yeah, it looks good to me unless I made a silly mistake somewhere. Exothermic, questions on it? If you can't draw the structures, you can't do this, right? Last thing for today, choose the molecule with the strongest bond. Which one has a stronger bond? HCl, HBr, HI, or HF?
HF.
HF. All we got to do is look at the bond energies. H with F is 565. Cl is 428. Br is 362. Now, let everybody think about this one. Actually, let's ask, why is this? Why does HF have the strongest bond? Possible student of the month question here.
Doesn't F have the highest electronegativity because it's top right?
Yep. So F has the highest electronegativity, and that means it's going to pull those electrons in closer and closer and closer, right? And as we go down, it gets weaker in electronegativity. Another problem with this is that if you look at HF, you might end up calling that what type of bond?
Ionic.
Yeah, it's very close, isn't it? At 1.9, right? So again, F, if it gets a hold of H, it is quite strong. That's why an acid called hydrofluoric acid, you would hate to get this on you. This is one, if you want to like basically wipe out a room, let's say that you were testing on animals with some type of virus, and that whole room got contaminated. You would fill the room with HF and basically kill all the animals, and you know, it would basically rust out the cages. Everything would be nasty, nasty. But HF itself, whenever you try to make an acid out of this, if you try to dissolve this in water, not very much of it dissolves because of this interaction here. It has, we'll get to this later, but it has a very low dissociation. I remember when we talked about net ionic equations last time, and we would say, if it were aqueous, we would separate them. Well, this wouldn't separate very well because it does not have a very big dissociation. That's what I got for today. If you have questions, by all means, get out of here. If you don't, but hopefully that's enough.
So the
weekend.
Hey, you too. Good day weekend. Hopefully we got you out on time, Emma. Bye.
Is the lab due Sunday? Basically, we have to turn it by Sunday, right?
If you turn it in on Sunday, that means I will not have it graded by the end of next week. If you turn it in before, I will probably grade them on Sunday, which would mean that, you know, if you turn it in before I start grading them on Sunday, yours will get graded.
Okay.
So you might have a 0 for a while if you don't get it in before Sunday.
Okay.
Yep.
What is the bond energy between H and I? On number 5.
You know what? That's the funny thing here. I didn't see it, but you know what it's less than? Can you tell me what it's less than?
565.
Definitely. Can you go lower?
Is it less than 149?
Probably not. So basically, if you're doing the bond between H and I, right? We know it's lower than 565. Cl is just below F at 428, 362 for Br. So it's probably lower than 362. I would say it's in the low 300s. But it is
Okay.
it's not on this sheet. Yeah, it's just not on here.
All right.
We could always look it up on the internet if we wanted to, though.
Have a nice weekend, Mr. Jackson.
Do. Questions?
Yeah, I have a question about what we did at the beginning of class.
You still on this SP stuff, huh?
I just don't understand a single thing about it. I'm just understanding like, what is it? Like, what is this? What is it called?
So it's basically orbital hybridization. So you know the quantum mechanics orbitals, right?
I don't think so.
SP and D stuff.
Yeah, I thought I did.
Okay. 1s2, 2s2, 2p6, 3s2, 3p6, all that.
Yeah, after that, I don't know anything about it.
All those things are designations for space around the nucleus. How much do you have? A few minutes? Like seriously?
Yeah, I have a few minutes.
Let's do this. Let's take a look. Space around the nucleus, right? So all an orbital does is it denotes space. So if this is an s orbital, right?
Mhm.
Here, I'm going to elongate this and call this an sp3 hybridization orbital. All right, but we don't even have to start there. We can start it off with sp1 or sp. So how can those electrons go around a central atom and keep apart from each other as much as they can? One on this side and one on this side, right?
Mm-hmm.
Imagine that the central atom is here. The electrons could be here around it or here around it, right? So this would be sp hybridization. All right. I don't have all white balloons, I'm sorry. So the colors of these has nothing to do with anything, okay? I just want to make sure that's there.
Okay.
So if we add another orbital, this is now sp2 hybridization, right? So how can the electrons now fit around each other? Trigonal planar. sp2.
So is that so? There's two p orbitals.
There's 2p orbitals used in this hybridization. In reality, the term hybridization means we're going to merge them all together, but we're not losing anything. So we take an S, which is normally spherical shape, and we take P's that are normally dumbbell shaped, and we reshape them. That's what hybridized, right? If something is a hybrid, it's in between the two. So we don't lose any of the number of orbitals. We still have 1 from the S, and we still have 2 from the P, and that's what gives us the 3. What's the electron for 3 round central atom? Trigonal planar. So 120, 120, 120, right?
So are these just the bonds?
Yeah, well, it's the spaces where the electrons are, which are the bonds. Right?
Okay.
All orbitals are spaces that can hold electrons. But we're talking about specific electrons that are being shared between 2 atoms, right?
Mm-hmm.
So now we're going to sp3 hybridization, right? Again, we're just keeping all 4 of the orbitals. So now we're going to have 4 places around the central atom where the electrons can be. With me? Watch what happens to our shape. Oh no. Try that again. If all of these are evenly around, can you see my shape here?
Yeah.
What is that?
Isn't that like it looks like one of those angular patterns, like a trigonal pyramidal.
We're not that far yet. How many do I have? sp3. So I have 4 regions where electrons can be. What shape is that?
The tetrahedral.
Tetrahedral. Right?
Yeah.
That's where all these things come from. Ready? This next one. We need another orbital. P only has 3, so where do we go for another orbital?
We got a D. D.
We go to D. Right? So watch what happens when I bring in another one and I spread them all out. Trigonal bipyramidal. Right?
Yeah.
sp3d. Last one, sp3d2. Oh no, it was my last balloon too. It just popped. Not gonna last very long, but if I put it right there, what do I have?
You have an octahedral.
You got it, right? So if we count them, sp3, it's falling apart. sp3, d2, right?
Yeah.
So again, what does all that mean? That's just fancy words for orbitals, which are spaces around the nucleus where the bonds can occur. If it's really giving you that much trouble, the only other way to really get this is just to memorize this chart right here. sp2 is trigonal planar, sp3 is tetrahedral, sp3d1 is trigonal bipyramidal, sp3d2 is octahedral.
So these orbitals have nothing to do with electrons.
There's
It's just
electrons are.
or wait, so is it does it deal with electrons or just the bonds?
Well, a bond is so if we break it down, a bond, right, is electrons being shared for a covalent bond, right? And that's what this refers to.
Yeah.
Right? The electrons are being shared and they exist in a space. The orbital is where the electrons are. I'm going to use a weird word. It's where the electrons are likely to be. During this sharing. So the bond is electrons being shared. The orbital, the s, these spaces, it's the orbital is the space where the electrons are most likely to be at any given point in time in this molecule.
All right, and then my next question was, how did you, you would just like name like SP3 or ST1 and like you would just like find an answer like a second later. How do you do that so quick?
It's counting.
What pattern is there?
So S is 1, and there are
Yes.
3, right? Take a look. I look at this.
Wait, is there?
I look at this guy right here. Actually, let's do this. I look at the guy in the middle, and I count the spaces where electrons exist around it. S, P1, P2, P3. This is undergoing sp3 hybridization. Here we have S, P1, P2, P3, P1. All right, S only has 1 orbital, P has 3, P has 5, but we're not going to need all 5. XE right here, S, P1, P2, P3, D1. So it's just counting. Take a look if we go over here. S, P1, P2, sp2. The double bond is just an area where electrons are. So that doesn't count as sp3.
Okay.
Again, if like these are the connections, but if you have something like this, I mean, trigonal planar is sp2. So that means if it's trigonal planar or bent, it's sp2. Tetrahedral is sp3. Again, the way you know this is by counting. If we have 3, even if it's 2 bonds and 1 unshared pair, that's still 3s plus 2p. If we have 4 bonds, 4 unshared pair, or 3 bonds and 1 unshared pair, or 2 bonds and 2 unshared pair, all of that added up is still 4. So that's s plus 3p's. How about trigonal pyramidal? What's a bipyramidal? What's it going to be?
That's going to be sp3d1.
There we go. If it's seesaw, trigonal bipyramidal, T-shaped, or linear, it's sp3d1. And the last one, octahedral, is going to be sp3d. This was sp3d1, right? And it was 5. So what is 6? sp3d.
D2.
D2. Boom.
Okay, that makes a little more sense.
Good, good.
I think. And then, That's all.
Sure.
Yeah, I'll probably have questions over bond energy because I still can't get my head wrapped around